So we're working on the second example in the notes that encompass section 3.2 through 3.5, and we're part way into section 3.5 because we did the first example already. So we're going to attempt to find all the zeros and find the complete factorization of this cubic polynomial. Our factoring techniques that we have before we knew the rational root theorem are not going to help because it's not quadratic. Can't be treated like a quadratic because this exponent is not double the middle term. Grouping won't work because we don't have 4 terms, so we're going to have to use the rational root theorem. So the rational roots are the ratio of the possible factors of the constant term divided by the possible factors of the leading coefficient. So the factors of the constant term are plus or minus 1, plus or minus 2, plus or minus 4. The factors of the leading coefficient are plus or minus 1. So the possible rational roots are each of these possible p-values divided by 1, so I get the same list as the p's. So that's 6 possible rational roots. So we could just start trying, but let's use one of our theorems, the remainder theorem, and see if we can narrow the field. So let's plug 1 into the function because it's relatively simple and see what we get. If we get a remainder of 0, we know that it was a 0. So I plug 1 in and I get 1 to the third, which is 1, minus 2 times 1, which is minus 2, plus 4. Add those up and I get 3. So that one is not a 0. Then I'm going to try negative 1. So plug negative 1 in here. Negative 1 cubed is negative 1. Negative 2 times negative 1 is positive 2, plus 4. Add those up and I don't get 0. So that's not a 0. Let's try 2. Plug 2 in. Still relatively simple. 2 cubed is 8. Minus 2 times 2 is minus 4, plus 4. That gives me 8. Also not a root. So I've ruled out 3 of the 6 already. Now let's try negative 2. I'm methodically going through them. 1, negative 1, 2, negative 2. So plugging in negative 2 here, and I get negative 8. Minus 2 times negative 2 plus 4, plus 4. That works out to be 0. Yes, I got one. So now I'm going to do synthetic division. So the coefficients are the coefficients of the polynomial 1, and notice the quadratic term is missing, so I need a 0. Negative 2, 4, and I'm using the 0 that we found was true, negative 2. Synthetic division, bring down the 1, multiply, add, multiply, add, multiply, write it down, add, 0. All right, we knew that was going to happen. And what I'm left with is quadratic. So I wrote down the quadratic because I started with a cubic, so my quotient is a quadratic. So 1x squared minus 2x plus 2. And let's attempt to factor, but it doesn't factor. Anything multiplies to 2 and adds to negative 2? No. So we're going to use the quadratic formula. So negative b plus or minus b squared is positive 4 minus 4 times a, which is 1, times c, which is 2. And now moving this way, 4 minus 8, right in here. So 2 plus or minus 4 minus 8 is the square root of negative 4 all over 2. The square root of negative 4 is 2i, so I have 2 plus 2i over 2. Divide the 2 through each term, and that gives me 1 plus I for the positive one, and 2 divided by 2 is 1, minus 2 divided by 2 is 1i for the other one. So I've got 2 complex zeros. So there they are. I have the first 0 we found, which was negative 2. And then these 2 complex zeros. So I have 3 zeros, and I have a cubic polynomial, so I should have exactly 3 zeros, so that's great. And now I want to, oh, we found all the zeros, yay, so we answered part A. And now we're going to find the complete factorization. So I want to write these as factors. I'm going to do the complex ones first. So factors can be written like x minus c, where c is the 0. So I can write x minus one of my factors, 1 plus x, and x minus another factor, 1 minus I think I said x, but that's an I. And then I'm going to simplify before I multiply, so distribute the negative 1, so that would be minus 1 minus I, and likewise in this one, x, so distribute the negative, so minus 1 plus I. All right, so here they are simplified. I'm going to multiply those out first, because I actually know that when you multiply factors and they are conjugates, that all of the imaginary parts are going to cancel and become real. Oh, I got ahead of myself. I was thinking of a different problem. Sorry, the question was to write it factored, not multiplied. So those two are the complex factors, so there they are. And then we also have the real factor, which was not as complicated. So our other real 0 was negative 2. So I'm going to write that as x minus negative 2, which is x plus 2. And so here it is in factored form. So we're actually done with this problem. If I multiplied it out, I'd eventually get back to what I started with, but we're not going to do that on this problem. All right, so moving on to the next one. So now we have directions where we know that we have a polynomial of degree 4 and it has these zeros, negative 2, 0, and furthermore, negative 2 has a multiplicity of 3. So first I'm going to write them in factored form. So when the 0 is negative 2, the corresponding factor is x plus 2, so minus negative 2. And it has degree 3, so it occurs 3 times. Sorry, multiplicity 3 degree, so it occurs 3 times. And then it also has a 0 of 0. So that would be x minus 0, so that's x. And that doesn't say anything about multiplicity. So if it's 1, notice I have a degree 3 times a degree 1, so 3 plus 1 is 4. So this has degree 4. So there it is. And these directions didn't say, but if you want it in standard form, you would have to multiply it out. So I wrote it out. I multiplied 2 of the linear factors first, and then I distributed the x through this third factor, and then I multiplied the trinomial by the binomial, and I wrote it up linearly. If you use the window method, that's fine. So this is the result. And that was all of the directions. So it took a few steps, but wasn't super complicated. So notice it has degree 4, and we started with the correct zeros and the correct number of them. All right, so now we have another example. First of all, let's talk about the complex zeros theorem. So if you have a polynomial p, and that references back to the polynomial that I defined earlier in the notes at the beginning of 3.5. So this is the form of a polynomial of degree n. So we're thinking about that from earlier. And it has real coefficients. Notice some of the theorems said complex coefficients. And if you have a complex number z, so complex numbers have the form a plus bi, then the complex conjugate, called z bar, is also a 0 of p. So if a plus bi is a 0 of the polynomial, then the conjugate is always also including not just complex numbers, but expressions where you have a radical. You keep the constant with the same sign, and you keep the term with the imaginary part with the same coefficient, but you switch the sign. So these are conjugates of each other. All right, so we're going to do an example. We want to find a polynomial of degree 3 with integer coefficients and a bunch of zeros. So I just want to remind you that if you know a complex root, then there is another complex root that is the conjugate. All right, so we have 2 zeros, and it's degree 3, so we need another one. But one of the zeros is complex because that's an I. So I know the conjugate of this is also a 0. So I know that this is another 0. So I'm going to multiply, first write them as factors, and then multiply them first. So if x minus 3 minus I, if 3 minus I is a 0, then x minus 3 minus I is also a 0. So x minus 3 minus negative I, so plus I. And then this is also a 0, so my corresponding factor is x minus 3 minus I. So there you go, my conjugate, my factors with my complex zeros. And then it also says we have a 0 of 1/2, so that would be x minus 1/2, that's a factor. If you wrote it without a fraction, you could just multiply by 2, but we can save that for later. So the first thing I want to do is multiply these two complex factors together. There's many methods for this, but I'm going to model it over here by using what I call the window method. So it's a trinomial times a trinomial. So I made a window that's 3 by 3, and I put the coefficients of this trinomial along the top, so x negative 3i, and I put the coefficients of this trinomial along the side, so x negative 3 negative I, and then inside each window pane I multiplied the terms on the outside, so x times x is x squared, negative 3 times x is negative 3x, I times x is ix, x times negative 3 is negative 3x, negative 3 times negative 3 is 9, and so on. And then, unlike polynomials where the terms are in standard form, so in that case, if the diagonals all end up being like terms, in this case, not exactly that, so we got to be careful. So these two are like terms, negative 3x and negative 3x. That's a constant, and these are complex, or imaginary actually. So ix and negative ix, those add up to 0, so I'm crossing those out. And over here I have some more imaginary terms, negative 3i and positive 3i, so those also add up to 0. And 9 is a constant, and over here I have negative I squared. So I squared is negative 1, times negative 1 is positive 1, which ends up being a constant. So I have a 9 and a 1. So I end up with x squared minus 3 minus 6x, and then constant term 9 plus 1 is 10. So notice my result here has only real coefficients and not any complex parts. And then I still have my other factor. So now I multiplied this out in 2 steps. So I distributed the x and wrote it here, and I distributed the 1/2 and wrote it here. At this point I could multiply by 2 and get rid of the fractions, but I didn't. I wrote it out the longer way, and I ended up with coefficients that were fractions, and it says integer coefficients. So in order to get rid of the denominators of 2, I'm going to multiply everything by 2. You definitely could have done it at this step, or you could have done it at this step. You could have multiplied this factor by 2 and gotten rid of the fraction right away. So at any point along here you can multiply by 2 to make sure you end up with integer coefficients. So multiply this entire expression by 2, and now I end up with a polynomial that has integer coefficients, and I started with these factors that corresponded to the zeros I needed, so this is right. Also, I want to point out back here, when you're multiplying a complex factor by its factor with the corresponding complex conjugate, the i's will always cancel out. So if they don't, something went wrong. All right, I think we're on the last thing. So another theorem, linear and quadratic factors theorem. Every polynomial with real coefficients, so not complex, can be factored into a product of linear and irreducible quadratic factors. So we know linear means like a x plus b, and quadratic factors, irreducible means that it's a quadratic factor, so irreducible quadratic means that it cannot factor with real coefficients. Doesn't mean it can't factor with complex coefficients. Now, it doesn't mean that it has to factor, if it was factorable, it doesn't mean it has to have integer coefficients. So you can't say, oh, I can't factor it with my, algebra 1 techniques, therefore it's irreducible. It's if you throw it into the quadratic formula, like you try to factor it, it doesn't work, and you throw it into the quadratic formula and your results have imaginary parts. That's when what you started with was irreducible. So here's an example. We have a quartic. Let's try to factor. So this looks quadratic. It looks like we could treat it like a quadratic, so let's try to factor it using that method. So if I treat it like a quadratic, it turns out x squared plus 4 and x squared minus 2 does in fact give me that. So that was a start. And now let's see if we can factor further. So I'm going to start with the x squared minus 2. It does not factor if you're thinking integers, but it does factor if you allow yourself to have non-integer coefficients. So we do this one by solving by using inverse operations. So I set x squared minus 2 equal to 0, add 2, take the square root, don't forget plus or minus when you take the square root of a square. So I have 2 zeros, and then I write them in factored form, so x plus the square root of 2 and x minus the square root of 2. Now I'm going to work on this one. This one does not factor with real coefficients, so it's irreducible. So this one is irreducible. So we did part A. Now part B says factor completely, so now I have to work on this one. So I'm also going to solve this one by inverse operations. So that set that irreducible factor equal to 0, subtract 4, take the square root of both sides. The square root of negative 4 is 2i, and it's plus or minus because I took the square root of a square. And then I rewrite those with their corresponding factors. So it would be x minus negative 2i, so x plus 2i, and x minus 2i. So that's the factor completely into linear factors. These are all linear with complex coefficients. I have some complex, they're actually just the imaginary part, but also complex. Let's check how many. 1, 2, 3, 4 factors, and we should have exactly 4, because that's the degree, linear factors.